theorem with wide-ranging application. It's a theorem about directed graphs. And a directed graph has a source node and a sink node and a one-directional edge that connects them. And that edge has a capacity. And that edge has a flow of information, water, electricity, goods going through that edge. A directed graph, by definition, is just a set of nodes and a set of edges. They don't even have to connect or even make sense, but then why would you use it? So if this edge had capacity 3, then the flow has to be positive and less than or equal to the capacity. The maximum flow is obviously 3. A cut takes the union of edges that connect an S set to a T set. S set is just a set of nodes that contain S, and the T set is a set of nodes that contain T, and their union is all the nodes. The cut is then the sum of those capacities. So in this case, the minimum cut is 3. Now let's do an example. We'll add a little more definitions and complexity. Add in 2 more nodes and some edges that connect it. Put in their capacities and max out some flow. At node 1, we have a mismatch of flow, but we're going to enforce the constraint that the incoming and outgoing flows have to match. So the flows have to be less than the capacity, and all the flow incoming to a node has to be the same as the flow leaving the node. Can't have any stagnant flows. The incoming flow to a node is the outgoing flow to a node for any node except S and T. S and T are a special case. There, the total outgoing flow from the source has to match the total incoming flow to the sink. This is called the value of the flow. Fixing the constraint at the nodes, so it has to be the minimum of the capacities at each node. Looking at the value of the flow, 2 plus 3. Looking at the cuts, add those capacities, adding those capacities, and so on. Minimum cut, same value. The setup for the cut is a little more complicated. We're going to associate variables with each edge, and we'd like them to be 0-1 toggles, so that when I multiply the y by the capacity, I'll get my cut value. So I want to minimize the capacity times a y value where I've separated the nodes into S and T. Well, then that means I need to define node values, so I know which nodes in S and which nodes in T. In terms of the y constraint, we're just going to make it positive for now, so 0 and 1 will both work. So every node will have a value assigned to it. We'll enforce that the source value is 1 and the sink value is 0. And then we want to propagate that 1 to all of the source S nodes. The y value is equal to the difference of the z's at the minimum. So we'll make an inequality, so it'll come down to it. So we have this constraint for all the edges going into the sink. Correspondingly, this inequality will be sharp at the minimum for the source. Replace it with its value, so it should satisfy this inequality. And this inequality will be sharp when it's minimized. All interior nodes will then satisfy the same thing, and this will do the propagation for us. At this point, it's not clear how everything's going to wind up to be zeros and ones. This requires a result on totally unimodular matrices, which I think we'll just invoke instead of trying to prove. With our problems defined, now it's time to put it in matrix form. Looking at the max flow problem, set up our flow variables, trying to maximize the flow value, which is the flow leaving the source, and set up our balance constraints at the nodes. All the flows have to be less than or equal to the capacities. And the flows are positive. I have two equalities for inequalities, so it's slightly different than what we've done before. It's a mixture of the two problems we've done before. Setting up our vectors. I'll order my right-hand sides, capacities, then equalities. And set up my matrix. Here's my four variables. My capacity constraints. My node balancing equations. So we have AX less than or equal to B for 4 of them, AX equals B for 2 of them. We've done both kinds of constraints before, so we know what the corresponding dual will look like in each case. Looking at the minimum cut problem, assign our node variables and node values, and our edge variables. We'll minimize the cut. The Y's are 0, 1 toggles, or they will be at the minimum. And set up our propagation equations. Propagating the sink value, propagating the source value. And all the Y's are positive. Rewriting it as a vector. Two zeros for the Z's. The first 4 components are positive, the second 2 components are unrestricted because they come from the equality constraint. Z1 and Z2 are unrestricted and the Y's are positive. lining up the source variables first, sinc variables last. And set up our matrix. The source 1 propagation equation, source 2, sinc 1, sinc 2. A transpose. Our dual equation.